welcome to this second lecture, or let's say a second part of the first lecture of this course. So I'm not very optimistic about the last lecture, I can tell you. Looking at the number of pages we have done in my notebook and the number of pages that already remain. But okay, we'll see to which point we go. And so what we have done yesterday at the very last moment was to establish the Gross-Pityevsky equation in the steady state. And as I said earlier, this is also called the nonlinear Schrödinger equation. You have kinetic energy, potential energy, interaction energy under the form of a mean field. And the term on the right side, which replaces the energy in the Schrödinger equation, is now mu, with mu being the chemical potential. And in fact, indeed, if you compute the energy of a state with n particles minus the energy of a state with n minus 1 particles, you find exactly this mu. When you do that, that's computing the integral, of course, of this guy multiplied by psi star. And the fact that this difference is mu tells you that the chemical potential is the price to pay to add one more atom in the system. Okay, so this is why this lambda, this multiplication factor is in fact written as mu, because this is the chemical potential. So what we will do now is finish the discussion about the solution for the ground state of the Gross-Pityevsky equation. And then we will introduce some dynamics. So an important limit into which we can solve this equation is the case where the interactions dominate with respect to the kinetic energy. And this is called the Thomas Fermi limit. So in this limit, we simply neglect the kinetic term h bar square over 2m Laplacian. And so if we do that, then the solution is really easy, because there is no differential equation anymore. You see that I can simplify the equation by psi, and I just obtain that mu is equal to g times psi squared plus v trap of r. And so psi squared, this is the density, because the integral of psi squared is the total atom number. So we can write psi squared as some density of r. And the solution is simply that the density is given by 1 over g times mu minus the trapping potential. So if the atoms are in a harmonic trap, which is a parabolic shape, the shape of the cloud is just the reverse, so an inverted parabolic shape. And so this is valid up to the point where the density is still large enough for this term, g times density, to be larger than the kinetic energy. So of course, So this is how it looks like. If this is V trap, and I give some value for mu, so this is mu, then at the center, if V trap is 0, the density is mu over G, so this is the maximum density. And then when V trap increases, density decreases up to the point where V trap is equal to mu, and of course, density vanishes and you cannot go further. And so then these points here are the limits, and the atomic density is given by this profile, n of r. Well, n of x in my case, because I have taken a cut. And so this point here is called the Thomas Fermi radius. That's the point where the density vanishes. And of course, the true solution of the Gauss-Pitevsky equation is a little bit different from this inverted parabola on the edges, because I have made the assumption that the term Gn is much larger than the kinetic energy, but here the density is 0, so it cannot be much larger than something else. So the true profile, in fact, is corrected on the edges, and so you have something that will decay a little bit more gently, and there will be no singularity on the edges if you have the true solution of the Gauss-Pitevsky equation. But this is a very useful method, this Thomas Fermi approximation, because in most of the regime, this is very well valid that the profile is essentially the inverse of the opposite of the potential. Of course, this is true also if the potential is not harmonic but more complicated. And then if your potential has this kind of shape, the cloud will have that kind of shape. And another point we would like to wonder is what is the size over which this correction applies? So over which kind of size do we have this situation? And this we can guess by looking at the solution of a very simple problem. So imagine you have instead a box. If I take the Thomas Fermi approximation for a box, this is very simple because now my V trap is essentially 0 and infinite on the sides. So I have mu somewhere. And so it means that the density, if I take Thomas Fermi, is 0, then maximum, which is mu 0 over G, and then 0 again. And of course, this is not very reasonable that the density of the cloud jumps suddenly from 0 to its homogeneous value. So there will be a region where the density connects between 0 and its average value. And of course, also the density at the center will be a little bit larger because you have to remove atoms on the side. And the typical size over which this happens is called the healing length. It's usually noted psi. And you find it, you can directly find it by solving the problem where V trap is 0, essentially. So you need to find the solution of second derivative of psi plus psi to the third power is equal to something. And the solution of this equation is essentially some arctangent function, a hyperbolic arctangent function, which connects between 0 and 1 nicely. And if you solve the equation, which is very standard, you find that the expression for this healing length is h bar over square root of 2m g and 0, or if you prefer, h bar over square root of 2m mu. And so this is called the healing length. A heal is when you hurt yourself, okay? And healing length is the length over which the condensate recovers from the hole it has somewhere. Okay. And so let me show you a couple of slides where the Gross-Pitevsky equation was solved numerically. C'est ça? Okay. So this is a solution in a box with no interactions. So if I remove the interaction term, of course, it's just the Schrodinger equation. So in a box, a ground state, Schrodinger equation is just the arch of a sine. And so this is the ground state in a box. Now let me introduce interactions. And so, of course, the atoms want to avoid each other, so they don't want to peak like that at the center. They want to occupy a larger volume. But still, on the sides, they have to recover from the zero condition. And so you have a central density now which is larger than n over L because the holes on the side, and a region with size psi over which it goes to 0. And if I increase more the interactions, of course, it's not, you have to equilibrate the price to pay to bend the wave function. So bending the wave function means having some Laplacian, so it means giving some kinetic energy, between the price to pay for the interactions, which is Gn0 or mu. And so if Gn0, if mu is larger, so then you want really to have the atoms go away, and then you reach this kind of situation where really the cloud is almost homogeneous with a tiny fraction on the edges that goes to 0 on the side psi. And as I said, the solution on the edge is a hyperbolic tangent. Okay, and now if I use instead a harmonic trap without any interactions, this is the central part here. The solution of the harmonic trap is just a Gaussian. And instead, the solution that would correspond to the Thomas Fermi solution is the dashed magenta line. It's very far from what we find. But if we increase interactions, then the profile broadens. And finally, if I increase it more and more, I find that it really nicely fits with the inverted parabola, except, as I said, on the very edges where it has to recover, and there is no singularity. There is a gentle connection to 0 with a size which is again given by xi. So I think that's it for the moment, yeah. And now we will introduce a time-dependent version of the Gross-Pitevsky equation. So this is section 3. Time-dependent Gross-Pitevsky equation and hydrodynamics equations. Okay, so let's start with writing the time-dependent GPE. So I will not derive it, but I will trust your intuition and start from what we have in the steady state. And of course, it's just like the Schrodinger equation. When you have some evolution of the ground state, what's happening is that you have e to the I e t over h bar. And when you derive it, that's why you get the e equals to e on the right-hand side. So the term that is time-dependent will replace this guy here. And the ground state solution will just be the same with some phase factor. But in the general case, it can also evolve if we are not in the ground state, such that the time-dependent Schrödinger equation is just the same one where I replaced the mu psi by e h bar d psi over dt. Okay? So this is very intuitive because now if I look for the ground state, psi is 0. It corresponds to the solution of the left equation. And when it evolves with time, it's just psi 0 of 0, e to the minus I mu t over h bar. And so if I use this one, the time derivative gives me back the mu, and psi 0 is a solution of this one. So now what I will do now is to transform this expression to study instead the condensate in terms of its density and its phase. This is called the Madelung transform. And these will give us the hydrodynamics equations. Okay, so if I want to write psi in terms of its density and its phase, what I do is to write that psi of R and T is the square root of the density of R and T times e to the I, the phase, theta of R and T. So this is equivalent. Psi is a complex wave function. So in fact, it lives in a two-dimensional space. And instead of having real part and imaginary part, I can replace that by two other real functions, which are the density and the phase. And now what I will do is to replace in the Schrödinger equation, in the Gross-Witkowski equation, psi by its expression in terms of modulus and phase, and derive equations for n and theta. Okay, so for this, I need to compute the time derivative of square root of n e to the I theta and the Laplacian of e to the square root of n e to the I theta. This term here will be really easy because this is n, okay? And this term here also is just a multiplication. So the difficult terms are those two ones. So let's do it. Let's be courageous. And what will be nice is to use, in fact, psi star times, for example, for the time derivative, I will compute this one. Because if I multiply then by psi star, every time I will have a psi times my psi star, I will get n, okay? So now, what is this time derivative, okay? I need to differentiate square root of n, and I need to differentiate also e theta. So this is equal to psi star, this is square root of n e to the minus I theta, times I h bar, and then times the time derivative, which will be, if I differentiate square root of n, I will have dt of n divided by 2 square root of n, and then e to the I theta. Remember, yesterday we differentiate square root of epsilon, and we know that the derivative is 1 over 2 square root of epsilon, so it's useful today. And the term with theta is just I d theta over dt, and then I keep my square root of n e to the I theta. Okay? So now when I multiply by this guy, these two will cancel, and these two will multiply and give me n. So I find, and all the e to the I theta, of course, they will cancel. That's the idea. I will have I h bar over 2 time derivative of n. And then the two i's, they multiply, giving -1. And so I will have minus h bar time derivative of theta times n. So this one is imaginary. And this one is real. So when I will then write the full equation, I will separate into real and imaginary. So I remember that the contribution from the left-hand side has one imaginary part and one real part. OK, so now let's go for square root of n, the Laplacian, sorry, of square root of n e to the I theta. So this one is a bit more tricky. So what is it? Psi star Laplacian of psi. This is psi star, the gradient, the divergence of the gradient of psi. And the gradient of psi, I have two terms again. So this is in the same spirit of that one. I have a term with the gradient of square root of n, and then e to the I theta, plus I, the gradient of theta, square root of n, e to the I theta. And now I have, again, to apply the divergence. And so this gives me the Laplacian of square root of n, e to the I theta. And then if I apply the gradient on e to the I theta, or the gradient on square root of n, I will have twice the same term. So I will have 2i gradient of square root of n, scalar gradient of theta, e to the I theta. So this is derivating this one and derivating that one. And now I have to derivate that one and also this one. So for this one, I have plus I, the divergence of gradient of theta, square root of n e to the I theta. And for this one, I have minus, because I and I, the gradient of theta squared, square root of n e to the I theta. OK, now I multiply by psi star. So all the e to the I thetas goes away. And I have some square root of n to get together with that. So this is square root of n, Laplacian of square root of n, plus, so this one I will compute. The gradient of square root of n is gradient of n divided by 2 square root of n. So the 2 goes away, and the square root of n goes away with this one. So it's just I gradient of n, scalar gradient of theta. And this one I will keep like that, plus I n, because of the square root of n, divergence of gradient of theta, minus n gradient of theta squared. Very good. And now what I will write is to identify the real part and the imaginary part. So this one is real. This one is imaginary. This one is imaginary. And this one is real. And the term I am missing now, the two last ones, these one, the other ones, it's just V trap n, if I multiply by psi star, plus g n squared. Okay, and they are real. Question? No? Right, so now let me equal the two sides, and I will start with the imaginary ones. So first, the imaginary part. On the left-hand side, I have I h bar over 2 dt of n. So I remove the I because the idea is that I take the imaginary part, okay? And this is equal to the right-hand side, the gradient of n. So I also have to multiply by minus h bar square over 2m. So minus h bar square over 2m. The gradient of n times the gradient of theta, minus h bar square over 2m, n times the divergence of the gradient of theta. Okay? So what I can see that there are factors of 2 everywhere below. So these ones I will remove. There is even one more h bar everywhere, so I will remove the square. And what I see that the important term is not really theta, but it is a gradient of theta. And I will define V, the fluid velocity, as h bar over m gradient of theta. So why do I say that it is a fluid velocity? Imagine you have a plane wave. The plane wave, you can write it as e to the I kr. And the momentum associated to this mv. So this time there is no gauge field, okay? It's just mv. It's h bar over I, the gradient of my psi. So when I take the gradient, the I goes away. The gradient of kr is k. And so this is h bar k. So this is well known. At the momentum of my plane wave is h bar k. And the velocity is h bar k over m. And so the velocity is also h bar over m, the gradient of the phase. The phase is kr. Okay? So this is very natural that h bar over m gradient of the phase is the velocity. And now that I have replaced gradient of theta times h bar over m by the velocity, what I find simply is that I have what is called the continuity equation. So time derivative of n plus, and so now I have gradient of n times v, and this is n times the divergence of v, which I can also write under the form the divergence of n times v. This is 0. So this is my first hydrodynamic equation, and this is called the continuity equation. It says that if you have some flow that goes through a surface, it has to be conserved, so there are as many particles that go on one side and the other. And so it ensures the continuity. So now let me go to the other guy with the real part. Right, so for the real part, so this I remove, it was just to explain you why I call it velocity. For the real part, on the left-hand side, I have minus h bar n dt of theta. So first, immediately, I mean, here, it's proportional to n, you see? And here, it's in, there is n, here where there is n, here there is n. Okay, here there is a, maybe I missed an n. No? Okay, that's like that. I forgot an n. Alors, attends, c'est où? Non, c'est ça. No, I think that's it, no? Is there something missing? Yes, you're right. Yes, that's why I don't have any problem. So I'm looking just at the real part. So what I will do is this guy to divide it by n. So here I will still have a square root of n at the denominator, but all the others, they are all proportional to n. So I will immediately divide everything by n, such that I don't write this, but I write minus h bar d over dt. Okay? And so what is the right-hand side? I have the terms I have to multiply by minus h bar square over 2m. So I have minus h bar square over 2m, the Laplacian of square root of n divided by square root of n. then I have minus and minus, so plus h bar squared over 2m, the gradient of theta squared. And in addition, I have the other easy terms, which are V trap plus Gn. Okay. Yeah? Because I have divided by n. Because everything is proportional to n except this guy, so I will still take n, but I have to put the square root of n at the denominator, otherwise. Okay, and so what I want are equations on the density and the velocity. So this is almost the velocity. This is 1/2 of m, the velocity squared. But here, to have the velocity, I need to take the gradient. So I will do that. And I will write that here, if I take the gradient, I have m times the derivative of the velocity. So I have m times the derivative of the velocity. I will put the minus sign on the other side, is minus the gradient of all the right-hand side, minus h bar squared over 2m Laplacian of square root of n divided by square root of n, plus 1/2 of mv squared, plus v trap, plus gn. And this one is a second hydrodynamic equation, and this one is the equivalent of the Euler equation for the fluid. So this is completely equivalent to the Gross-Pitarevsky equation, except that now we are speaking in terms of velocity and density. And this also gives us a nice intuition on some terms that we may want to ignore if we make some approximation. So this, if now we look at this term, this is a kinetic energy corresponding to the motion in the fluid. This is a trapping potential. This is an equivalent of some pressure due to the interactions. And this guy here is called the quantum pressure . And if I consider the velocity as the velocity of a classical fluid, you see that in the equation that the only point where h bar is explicitly present. And h bar is there. This one is the one which is responsible for bending the wave function and all this psi. It describes the fluid at the microscopic scale when there are some defects. But globally, if we want to look at the collective behavior of the gas, typically, we can ignore this term. And ignoring this term is called sometimes a hydrodynamic approximation. So if you describe the fluid as simply hydrodynamic, you can sometimes neglect this term. So of course, at equilibrium, what's happening at equilibrium? At equilibrium, nothing depends on time, and even the velocity is 0. And so at equilibrium, we just have this gradient of this one, and this one being 0. And as it is 0, this gradient, it means that all that guys are constant, and of course, they are equal to mu. And this is just the Gross-Pitarevsky equation at equilibrium we had before. Okay? right. So what we will do now is to look a little bit what's happening when we go out equilibrium and derive the collective modes of the gas, either for the uniform case or for the trapped case. And so we will look at excitations of the gas. And we will start with wave-like excitations. In the uniform gas. So uniform gas means V trap is 0. And the solution for the equilibrium case is just that the density is homogeneous and is equal to mu over G. And we wonder what's happening when we go a little bit outside of this situation by perturbing a little bit the density and the phase, well, and the velocity. So we look for small deviations. Now, this is at equilibrium, okay? Out of equilibrium, we write the density as being this N0 plus some perturbation delta N depending on position and time. And there is also a V which is 0 at equilibrium. And so it means that V itself it's small and depends on position and time. And what we will do is to write the hydrodynamic equation using this form and assuming that V and delta N are small, such that we write them to first order. So if I start with the, so let me write, I will call them 1 and 2, these equations. 1 is a continuity equation, and 2 is the Euler equation. So if I write equation 1, and I assume that delta N and V are small, what should I say? So the time derivative of N is only the time derivative of delta N because N0 is constant. So I have the time derivative of delta N plus, and then in this expression there is already V, which is of first order in VL delta N. So I have to take the 0th order for N, which is N0, which is constant. And so it goes outside the divergence, such that I have N0 divergence of V, and this is equal to 0, to first order. And then for the other one, I have to look at what is the expression of square root of N, which is square root of N0 plus delta N. And so this is approximately square root of N0 plus delta N over 2 square root of N0. So in my equation here, I have M. So equation 2, it will give M time derivative of V is equal to minus the gradient of what? So the when I take the Laplacian, the Laplacian of square root of n0 is 0 because it is a uniform system. So I will only have a Laplacian of delta n, such that the numerator is already of order 1. So for the denominator, I have just to take n0. So it's minus h bar square over 2m. My denominator, which is delta n over 2 square root of n0, and my numerator, sorry, and the denominator is just square root of n0. Then this term is of order 2. It's v squared. I forget about it. And I have v trap, which is still there, which is 0, sorry, because it's a uniform case. And then the g is g n0 plus g delta n. But at the end, I will take the gradient. And so this is constant. So the gradient of this guy will go away. So now if I replace again, I find that it is minus the gradient of h bar minus h bar square over 2m delta n over 2n0, so over 4m delta n over n0, plus g delta n. Okay, and what I will do is to look for wave solutions under the form delta n is some amplitude e to the I kr minus omega t, and v is some v0 e to the I kr minus omega t. Yes, you are right, of course. Much better. Otherwise, I will be in trouble. So, okay, so the interest of writing it that way is that my derivatives become very simple. Time derivative gives me minus I omega, and gradient gives me ik. And now I will derive what is the wave equation for this. So what I do is to take the second derivative, the second time derivative of this one first. So the second, let me first write it. So I take the second derivative of delta n, and then I have n0 times the gradient of the time derivative of v. And the time derivative of v is this one. So I have n0 and then minus over m up. And then I have the Laplacian of my parentheses, minus I square over 4m, Laplacian of delta n over n0, plus g delta n. Okay. Perfect. So now I replace everything by these expressions. And I will notice that I have n0 here and n0 here, so they will cancel. And here I have n0 and g, so this will give me the g and 0. And I find that minus omega squared delta n equals to 0 is in fact equal to minus k squared over m And then I have already the minus and the second derivative. So this one is h bar squared k squared over 4m. The n0 cancels. And here I have plus g n0 delta n. Delta n also here. So all the delta n's go away. I can change the sign. I have a minus on each side. And I find the dispersion relation for these wave excitations, which is called the Bogoliubov spectrum. And which is omega squared is h bar squared k squared. Okay, let me write h bar squared omega squared, okay? H bar squared k squared over 2m squared plus g n0 h bar squared k squared over m. So the energy is not simply, if I take the square root, it gives me the energy. The energy is not the energy of free particles, but there is also this term which corresponds to interactions. So there are two regimes, depending if k is small or k is large. At small k, then k to the fourth is very small as compared to k squared. And if I take now the square root, I will find that omega of k is simply c times k, where c is the speed of sound and is square root of g n0 over m. So at small k, I have sound-like excitations with a linear dispersion relation, and the speed of sound is in a square root of the chemical potential. And then at large k, of course, it corresponds much more to free particles because the k to the fourth term dominates. So what do I have exactly? I will look at h bar omega. Then as it is large k, I can factorize this one. I will have h bar squared k squared over 2m. And then I have 1 plus g n0. And if I do this, I have to put here 4m over h bar squared k squared. So if this guy is small because we are at large k, this is approximately 1 plus 1/2 of this one. 1/2 of that, I will have 2m divided by h bar squared k squared, which is exactly cancelled with this one. So this is approximately h bar squared k squared over 2m plus g n0. Or if you prefer, h bar squared k squared over 2m plus mu. Whereas here, I can also write as a square root of mu over m. So you have free particles, but they live on top of the chemical potential, which is there because of the atoms in the condensates. And so it's a parabolic dispersion relation just as free particle, but the energy is offsetted by the presence of the condensate. Okay, and something I would like to show you before showing the slides is the consequence of having this linear dispersion relation at small momenta. And this is a first criterion for superfluidity. The existence of a critical velocity. And this is the Landau approach. So why am I saying that the fluid is a superfluid? That's because if I try to create some excitations, it will not work unless the fluid has a velocity larger than some critical velocity. So imagine you have the fluid going to a pipeline like that. And there are some little defects on the edges that may scatter with the fluid and then eventually damp the motion. And this can lead to some loss in the conduct. What are the conditions to create some excitation? And so as I consider really a fluid going through a pipe, so it is a problem that is invariant by translation. It means that both energy and momentum are conserved. So before the excitation of some particle, I have an energy which is 1/2 of mv squared and a momentum which is mv. And after, I need to create an excitation that will change the fluid velocity. So the new energy will be the energy of the fluid modified by the fact that we have some excitation. Okay, I should write it that way, but it's the same. Plus the energy of the excitation. And the momentum is now the new velocity, mv, mv prime. Okay, I go too fast. Okay, I have the new velocity of the fluid, which is 1/2. The energy is 1/2 of mv prime squared, plus the energy corresponding to creating an excitation with momentum p star. And the momentum is mv prime for the fluid plus p star for the excitation. And so as energy and momentum are conserved, if I look at the conservation for momentum, I can now deduce that v prime has to be v minus p star over m. And I inject that into the conservation of energy, and I find that 1/2 of mv squared should be equal to 1/2 of m v prime minus p star over m squared plus my energy of p star, which is at low momenta, it is c p star. And so now if I expand this guy, I will have the 1/2 of mv squared that disappears. And so 0 is equal to minus v scalar p star plus cp star plus p star squared over 2m. And so as p star squared over 2m is positive, this is greater than Cp star minus Vp star. So what I find is that this is possible only if V scalar P star is greater than Cp star. So this is if I write it under the form V scalar U greater than C, U is a vector with a unit momentum, unit modulus, sorry. So it means that my velocity along this axis should be larger than C. So the best choice is to have a V already along the direction of the excitation, but still the velocity of the fluid should be larger than C, otherwise I cannot create excitations. So this is a superfluid with the Landau criterion on the velocity in the sense that there exists a critical velocity below which you will have no dissipation. And so let me now illustrate what I have just said with a couple of slides. Okay. So this is what we have done. And we have written the dispersion relation for the Bogoliubov modes and identified the speed of sound. I forgot to mention that these two regimes, where are they? Large K and small k. What is large, what is small? Well, it depends on the relative weight of these two terms. Large means K limit should be greater than G n0 times m, essentially, or 2m, let's say. So this means that this limit situation between two things are when we have, there is a square root, 2mg n0 over h bar, and this guy here is written, it's not written anymore, but it's the inverse of the speed of sound, of the healing length. So if k is smaller than 1 over xi, it's small k regime. If k is greater than 1 over xi, it's large k regime. Okay, and this is how it looks like. At small k, it's linear with k, with the speed c. At large k, it goes very close to the red line, which is a parabola shifted by mu. And the limit between the two regimes is given by xi minus 1. And this has been tested experimentally, this relation, in the group of Near Navidson in 2002, using Bragg diffraction to look at what are the conditions to create excitation. And he indeed showed that the spectrum is really in very good agreement with what is expected from the Bogoliubov theory. This is a criterion for Landau superfluid velocity, and this graph here is an experimental test of this critical velocity. This one is, there are several experiments, okay, who have seen that. Maybe the first one is one by Ketterle. This one I like because it's really clear what's happening. Yeah.
You said that we just turn on our potential curve. So there's a relation to have this critical velocity or not? I mean, we turn on our potential, and if k is too high, I will see this like excitation particle, as you said.
So. It is true that this Bogoliubov dispersion relation, as it is written there, you know that I have written excitations under the shape of waves like that, which means that I have assumed some translational invariance. and that the plane wave are good wave functions. And so this is what I have assumed to derive that. So this is really the dispersion relation for the homogeneous gas. So if you don't have a homogeneous gas, which was the case here, it was in 2002 only, there were no uniform gases produced for the moment. And what happened is that they did the experiment in an elongated trap, but it was still a trap. But it means that the density varies a bit slowly from the center. And if you concentrate on what is happening in the center, then you still can see some sound waves, even if on a larger scale, it is not true anymore. And this is exactly, in fact, what this zoom tells. This zoom tells that if you really look at, okay, so at small case, you have, you should have this linear law, but the gas is not infinite. It has a size which is R. So you cannot have waves that have a wavelength which is longer than R. It's not meaningless it's meaningless, in a trap. So there is a cutoff at small k, which is 2 pi over R, and which is the one they look at in the zoom. And this is to show you that in this particular experiment, this 2 pi over R is very, very small as compared to what they probe. So they have a cloud which is long enough for this R to be very, very large, and there are still lots of waves that can survive in this elongated cloud. So this is a very good question. Normally, this is just for the homogeneous case, but in many cases, you can still have sound waves, even in a trapped gas, if the period of the sound wave is smaller than the size, really smaller than the size of the gas, essentially. When you go to the end now, it has to change a little bit its nature. So it's true that if you want to be really precise, you need to solve really the Gauss-Pitevsky equation, time dependent, etc. Okay. So this is the Landau criterion, and so this experiment is done, in fact, it's done in a 2D gas. And what they did is to drag a laser beam at constant distance from the center, around the center, just has to have always the same density around to kind of mimic a homogeneous gas. And they were wondering at which speed they have to rotate this laser beam to create excitations. And they measure the excitation as an additional energy given to the cloud that they measure after a time of flight. So they measure the heating of the cloud. And what they see that if they drag their beam slowly enough, they do not excite at all the gas. Only when they drag the beam above some critical velocity, some excitations are given to the cloud with a quadratic evolution in agreement with kinetic energy, essentially. So this is a nice illustration of the existence of a critical velocity in a quantum gas. Okay, this is the end of this section. And now I would like to discuss another kind of excitation. Still in the homogeneous case, which is not described by this wave. Here I have restricted myself to some excitations which are kind of wave-like. And so this is not, okay, that was another one. This is not always the case. And there are excitations that are not wave-like, and for which I cannot say that delta n is small, because I can even have the density go to 0 due to this excitation. And so it's not described by this kind of weak excitation. And namely, this excitation I would like to introduce are vortices. Okay, so to introduce these vortices, we can remark, I've just removed it, of course, but that the velocity everywhere it is properly, the phase is properly defined, is a gradient of the phase. So normally, if you have a field psi, there is no problem to define a phase, except if phi is 0. Because if phi is 0, you can choose anything you want for the phase. It's not important because the term in front is square root of n is 0, so the theta is not properly defined. So everywhere where psi is not 0, or if you prefer, where the density is not 0, then the velocity is well defined, and we can even take the rotational of the velocity. And of course, if we take the rotational of a gradient, we find 0. So everywhere there is some fluid, the flow is irrotational because the rotational of velocity is 0. And what will, imagine we have maybe some defect where the fluid may vanish, and we look at some contour around this point. So on each of these points, the density is not 0, okay? There is some density everywhere. And what I will compute is the circulation of the velocity on this contour. So everywhere there is some velocity. I don't know, it is like that. Here it is there. Each point there is something. And when you take the integral over a contour, you need to take the integral over the tangent everywhere, so your dl is like that. Very good. So this, in fact, will be very easy in our case because v is a gradient. So it's already some derivative. So integrating a derivative is something easy. So what do I find? So I have h bar over m and the integral over the contour of the gradient of the phase dl. So this is simply the phase taken between one side, the end of the contour minus the beginning of the contour. But if I start from one point and I take the integral, I come back to the same point, okay? So it should be almost the same value for theta, except that, of course, my phase can be defined within any multiple of 2 pi. So I am allowed to have a certain number of times 2 pi here that I will call q, where q is any integer, positive or negative. Okay, so now I have h bar times 2 pi, this is h, such that the integral over a contour, the circulation of the velocity is q, which is an integer, times h over m. So you see that the circulation is quantized. In units of h over m, which is a quantum of circulation. So if this is true for any contour around m. So if I can deform this contour and put it to a size almost 0, of course, if there is no singularity in m, I can also shift a little bit this contour. I should find the same thing, and then the value is 0, essentially. But if there is no density around m, I am not allowed to do that. It's a topological problem. I am there, and I just cannot go away. And so in this case, there could be a singularity with the density going to 0. And some circulation non-zero around this point. And this is what a vortex is. And Q is called the charge of the vortex. Okay, so we could even evaluate a little bit what's happening around that vortex if Q is non-zero. So the simplest thing to imagine, if we have a vortex, to get a given circulation for the velocity around m is to imagine that the velocity is always the same on the contour. So if I take a circle of radius r, and I imagine, okay, the velocity is always the same, it is parallel, it is tangent to this circle, and it is just some value that may depend of r times e theta. And so when I take the integral, my dl is just, okay, let me call it E phi, otherwise I will have some problem. So this angle here I call phi. dl is just r d phi times E phi. And so Q times h over m, which is the integral over the contour, is the integral, the sum between 0 and 2 pi of r d phi, the scalar products remove the E phi, times v of r. So it does not depend on phi. In fact, it's just 2 pi r v of r. And what I find is that to have this kind of velocity field, I need to choose v of r, which is equal to h divided by 2 pi, which is h bar. So q h bar over mr. So the velocity goes around the vortex, and it scales like 1 over r, which means that when you approach the center, the flow is quicker and quicker. And of course, on which side will I have problems of going too fast and losing superfluidity, and maybe I should wonder on which side the density will drop. So this will give me the size of the vortex. And the answer is when the velocity reaches the speed of sound. And so it means that I have, so let me take Q equals to 1 to simplify, a vortex of charge 1, I will have h bar over m d is equal to c, which means that d is h bar over mc on the order of that. And in fact, this is psi, because if I replace c by its value square root of mu over m, I find that this is h bar over square root of m mu. And this one is square root of 2 psi. So this is a good order of magnitude. So the size of a vortex is of order psi. This is approximately psi. And then around this region where there is no fluid, everywhere else there is fluid, with a density which is approximately n0. And here we have a drop of the density on the size psi, and the fluid that turns around. So if I make a cut, I will have some fluid, and then chook, density goes to 0 on the size psi, goes to n0 far from the center, and this guy is approximately 2 psi. Okay. And last remark. So the typical energy for a vortex so of course the energy of a vortex is essentially in the velocity of the flow. So it's essentially kinetic energy. And then you can integrate it over ddr in dimension d. But this is proportional to q squared. So if you have a vortex of charge q, then the energy is like q squared. Whereas if you have, with the same velocity, q different vortices, then the energy is q only. So this is q squared times the energy of a single vortex, because it goes like v squared. Whereas if you have q vortices of charge 1, the energy is just q times the energy of one vortex. So it's much more energy to have one vortex of charge q than to have q vortices of charge 1. And so in general, the vortices with a charge larger than 1, they decay into multiple vortices. So let me show you some slides. Yeah, so this is about vortices. This is a profile for the wave function of the condensate in the presence of a vortex. So it decays linearly with the distance to the core. It is 0 in the center, of course. This is for charge 1, and for charge 2, now it's slower, etc. So the size is larger for a larger vortex. This is the velocity field, and as I said, L larger than 1 is unstable, and what's happening when you have multiply charged vortex, in fact, it decays into a lattice of vortices, vortex lattice. And this picture is an example of taken in my lab, when what we do is to rotate BC. And when a BC is rotated, it likes to have vortices, because then the velocity field also has some rotation. And the faster we rotate, the more vortices we can have in the sample. And here you have a full lattice of vortices in this example. Okay, and I have a last point to do. So we are at what time did we start? Okay, I will at least write the equations. The last point I wanted to make, but maybe I will do it with the slides in this case, if I have the slides. Yeah, okay, I have more or less the slides. So if you want more detail. Là, c'est éteint ou allumé? Je ne me rends pas compte. Voilà. So this is the last point. So this is the number 6. I'll at least write that. And this point is collective excitations in a trap. Because what we have done up to now is to look at uniform gases. But what's happening in a trap when the trap is not very shallow and we cannot really say that we identify a long direction along which we have these uniform-like waves, as with your question. So if we are in a trap, we also have a situation where there are specific collective modes. And what we do to find them is to neglect the term corresponding to the quantum pressure in the hydrodynamic equation. Because, of course, this one describes very tiny stuff. And when we look for the cloud as a whole with its Thomas Fermi distribution, big radius, etc., and we look at at large size excitations, then we can neglect safely this h bar square over 2m, Laplacian of gradient of n, etc. And we are left with an equation where we only keep, this is not working very well. Okay, we only keep the terms like, yes, this one in blue, and these ones, these three ones, okay. And so what we can write if we play the same trick as we did for the Bogoliubov modes, okay, we consider that it's small change in n and a small velocity. We linearize everything, but after removing the h bar square over 2m term. And what we get is an equation that is written in the second part of the slide, where the frequency of our excitation is related to the divergence of mu minus v over r divided by m, etc. And in fact, if you remember, the speed of sound is square root of mu over m. And now, if we look to which value omega is proportional, it's proportional basically to something like square root of mu minus v of r over m. And so this is the local chemical potential. In the center, we have the maximum density. So if I compute the speed of sound, it will be square root of mu 0 over m. If I go a little bit to the side, the density is a bit less. It is a bit less like mu minus v over r. And there, I can locally decide that, OK, let me consider this density as being my density and recompute the speed of sound with this density. And in this case, I will find the square root of mu minus v of r over m. So it's a kind of local speed of sound. And the modes, I will find them by solving this equation. The second derivative with respect to time of delta n is equal to the divergence of the local speed of sound squared times the gradient of delta n. And so I can solve that. So for example, if I have isotropic 3D trap, everything is rotationally invariant. So the natural basis on which I should solve this problem is the basis of the 3D spherical harmonic functions. And so I introduce a function that varies with R only, which is a polynomial, and then the orbitals, YLM, which will describe all the rotations. And I can express the eigenmodes of my BC with the quantum numbers, which are the radial excitation, NR, and then the angular momentum, L. And in fact, it's the same frequency for all modes M, which have the same projection L of the angular momentum. So this is the solution in 3 dimensions. In 2 dimensions, I can do exactly the same trick, except that instead of a 3 here, I have a 2 there, but it's the same kind of solution. And this is a spectrum for a 2D gas in a trap. So the good quantum numbers are the radial excitation for the quantum number, and R, and the angular quantum number, which is little m. And so the spectrum is given by that. So there are several branches. Each time you increase n, you have lots of m possible. So these are the spectrum you find for different values of the quantum number m and for different branches with different nr. So the red line here corresponds to what is called surface modes, corresponding to when m is relatively large. Large m means that you have, in your mode, you have some symmetry of order m. So a mode with m equals 2 will have 2 maxima and 2 minima around the cloud. A mode with m equals 20 will have wiggles, 20 little wiggles on the side. And so here is an example, in fact, in a ring trap, but you also have this kind of surface modes corresponding to m equals to, I don't know, maybe 20 or something like that. This guy is doing, okay, silly things. So this is to know what is the critical velocity in your gas, in a sense, you have to look at the tangent of this excitation spectrum, and this corresponds to the critical rotation velocity to induce the first surface modes, this red line. I will zoom on these 3 dots here, which corresponds to collective modes, which are very specific and interesting collective modes. So this red dot here, the red dot corresponds to have no radial excitation, n equals to 0, so this is the first branch, but having m equals to 1. So m equals to 1 with n equals to 0 means either rotating in the 2 directions or having a center of mass motion along the 2 directions. So this is just the center of mass mode, and there are 2 of them because I can oscillate like that or oscillate like that, or equivalently rotate to the left or rotate to the right. This is why it's m equals plus 1 and m equals minus 1. This is rotating to the left and the right, and the x and y oscillations are a superposition of these 2 m equals plus minus 1 with plus and minus sign. So this is easy. Any gas has that in a harmonic trap, even your thermal gas, even a single particle. It has a center of mass motion. Then you have the monopole mode. So this one, I will come back to it, hopefully, discussing the 2D gases, because it's a very important and very nice mode. What does it correspond to? You have nr equals to 1, so 1 excitation in terms of the radial motion, and m equals to 0, so no wiggles at all on the sides. So this is also called the breathing mode. So it's called the monopole or the breathing mode. You have your cloud, and it breathes like that. So the radius oscillates in phase for all directions. And so this corresponds to this blue dot here. And in a 2D gas, this frequency is equal to 2 times the trap frequency. whatever the amplitude, and this is one of the consequences of a nice property of 2D gases. So this mode, it can be used to probe the equation of state of the gas because it's also a compression mode. You have the gas which is strongly compressed and then dilated, compressed, dilated. So if you have some specific equation of state, it will influence the frequency of this mode. And then the green dot here, the green spot. It's painful. Okay, you see it. This one has NR equals to 0. It is in the first branch, so there is no change in terms of the density. But M equals plus minus 2, so it is deformed like that. So the 2 maxima and 2 minima around the cloud. And there are 2 modes, M plus 2 and minus 2. It means that you have a deformation of the gas, and this guy rotates in one direction, or the same deformation rotates in the other direction. This is in terms of M. But I can also make the superposition of these 2 modes, and then instead of rotating this deformation, what will happen is that this deformation will change its eigenaxis. So I will deform like that, and after half a period, my glass will be like that. So this is this kind of mode. And so this one is a quadruple mode. And this one is very important because you don't have it in a thermal gas. It's really another signature of superfluidity. So if you are with a trap, instead of measuring the speed of sound and this critical velocity, etc., you can also evidence that you have a quadruple mode, and this is a signature of superfluidity. And another nice mode that does not correspond to an isotropic trap, but is present when you have a trap which is with different frequencies along X and Y, so already your trap produces elongated gas, is a scissors mode. So the scissors mode is when I have the main axis of my trap like that, for example, I tilt the cloud, and then I will have this kind of oscillation, so like a scissors. That's why it's called a scissors mode. This oscillation is also present in the nuclei of atoms. And this one also is there only for superfluids. So it has been used to probe the superfluid nature of Bose-Einstein condensates. It's related to the quadruple, so that's why I've taken the same color. This scissors mode, when you go back to some isotropic cloud, it connects to one of the quadruple modes. And so this is the first evidence of this scissors mode that has been measured in the group of Chris Foote in Oxford, where what they did is to have an elongated trap, to tilt suddenly the main axis to observe the rotation. And this is what happens, This is what happens if the gas is thermal. So if the gas is thermal, there is no really a mode that corresponds to doing that. When you do that, you excite both the motion x squared and y squared. And they oscillate, but with different frequency, because one is in omega x and the other one is on omega y. So there is a bit note between these frequencies. And if you look at the main axis, it does strange things. Whereas when you have a superfluid, so below the critical temperature, then the cloud, as a rule, evolves like that, and you see just one frequency, which is the scissors frequency. It is equal to square root of omega x squared plus omega y squared. And I think, okay, this is my summary for the first lecture. What we have seen is that BC occurs if the number of atoms I can put in the excited state cannot exceed some upper bound. In this case, there is a saturation of the excited state. So this happens in a 3D box. This happens in a 2D or a 3D harmonic potential. We have derived the Gross-Pitevsky equation using the mean field approximation. We have shown that in the time-dependent Gross-Pitevsky equation is equivalent to hydrodynamic equation with a continuity equation and a Euler-like equation. We have also shown that a weakly interacting Bose gas is superfluid with the existence of a critical velocity for the excitation with the Landau criterion, and presents on also specific superfluid excitations in the form of vortices and eigenmodes for a trapped BEC. So a comment on superfluidity, it is a property that is related to the motion of the fluid. So if you want to be sure that the fluid is superfluid, you need to make an experiment that proves the dynamics of the fluid. And so next lecture, we will discuss two-dimensional Bose gases and the Berezinski-Kostelet-Thouless transition. See you tomorrow.